Alrighty, guys. Thank you for meeting me here today and being patient with me as I'm just a little bit behind my normal schedule today. But that's okay, not the end of the world at all. I know we are still waiting on those videos from Yiping's lecture to be posted. I am going to get those up in the modules. I just have not had time to do that yet, but I will do that later today. We'll see. Let's get into it. This is MAC2311 section OH1, which is top line arms. And today is the 1st of September, 2021. We have two sections to cover today. First, we want to talk about continuity, which is a big deal. We're going to see exactly what it means to say a function is continuous. And we're also going to talk about limits at infinity. And this is section 2.6. And both of these sections will have some opportunity to revisit the concepts from 2.4, the delta epsilon stuff. So rather than reverting back to 2.4 and working problems from that section, I just want to continue using that language and notation as we move forward into section 2.5. So that's what we will do. So question, what does it mean to say a function f is continuous? This is surely a word that you guys have heard and used in the past. We use the word continuous a lot in pre-calculus. What does it mean?
It means that there's no interruptions to the line or sequence of points.
Good. No gaps, breaks in the graph. That is our intuitive notion of what continuity is. No gaps or vertical asymptotes, no breaks. The graph is one connected piece. And as a global statement, this is accurate. This is correct. A function f is continuous everywhere if its graph is a single unbroken connected piece. But what does it mean to say what if I want to look one point at a time? What does it mean to say f is continuous, say at x equals 2? So at a particular x value. This becomes a little bit trickier because our notion of continuity that we carry from previous classes has to do with the function as a whole, the graph as a whole. But if I want to look at just one little part of that, one particular point, what does it mean to say that a function is continuous at one particular number, at one particular input? I can't compare to the graph as a whole because I'm focusing just on a local property. But we do have some idea of what it means. It means that whatever's going on at x equals 2 shouldn't mess up this whole thing. right? So whatever it means to say f is continuous at x equals 2 should be consistent with this idea of what it means to say that f is continuous everywhere. So in particular, if you're continuous at x equals, or if you're continuous everywhere, then certainly you should be continuous at x equals 2. And if you're not continuous at x equals 2, that should mean you're not continuous everywhere. So here's what I'll say from an intuitive perspective. Whatever is happening at x equals 2 shouldn't create any gaps or breaks in the graph. So I can't talk about a single point being connected, like a single solid piece. It's just one point. Of course it's connected. It is just itself. So kind of we answer the question in the contrapositive by saying, okay, well, if you're going to be continuous at x equals 2, that means whatever is going on at x equals 2 has to be consistent with being continuous everywhere, which means connected, no breaks, no gaps. Turns out there's a very nice way to describe this. So let me draw a picture here. Okay. Do we want to connect those? What was I doing? Let's see, we have that straight over there. I can make that one. One like that. Yeah, let's do it like this. We join this piece to that piece like this, and then I'll something like this over here. Okay. Yeah, so just a silly toy example. Definitely, here are some things that are not looking so nice. Maxwell, stop that shit, puppy. No. This is certainly not behavior that we would call continuous because it creates a gap, a break. This is behavior that we would not want to call continuous because again, there's a disconnected piece, right? Most of the graph is over here and then there's a disconnected piece down there. That's not continuous. And whatever's going on over here, we wouldn't want to call that continuous either because again, that creates a break. Here's one piece of the graph and a separate piece of the graph. And label these as just A, B, C, and D. So we want to say that the function is discontinuous at A, C, and D. Each of these have a special name. At x equals A, this is a jump discontinuity. At x equals C, this is what's called a removable discontinuity. we say it could be removed because if I just reassign the function value at C to fill in this hole, that would fix the discontinuity. And at x equals D, we would call this an infinite discontinuity. At x equals B here, we're continuous. And what I want to do is kind of just think about how we could express that in terms of the notation that we've used so far, limits and stuff. So here, the left limit is different from the right limit. Yeah. As I approach a from the left, I'm going to one y value. As I approach a from the right, I'm going to another y value. So the kind of thing that's going wrong here is that the left limit and the right limit don't match. So the overall limit here wouldn't exist. So maybe having the limit exist is a necessary criterion for being continuous. And then we look over here. I don't want to call this behavior continuous. It's not. But here the limit as x approaches c of f of x would exist. The left behavior and the right behavior are the same. The value of that limit would be whatever the y value of this hole is. But I still don't want to call this continuous. So having the limit exist is also not enough to guarantee continuity. You do need the limit to exist. But beyond that, I would also need this guy to be at the same height as this guy. That's what would fix the intuitive discontinuity. And what that would mean is that we need the value of the function to match the value of the limit. And it turns out that is the definition of continuity that most calculus students see. So by thinking about what makes a discontinuity, we hypothesize the following. F is continuous at, say, x equals a, not this a, but just number a in general, if and only if the limit as x approaches a of f of x exists and is equal to the value of the function there. And for Calc 1 class, this is usually taken as the definition. So in short, you need the limit as x approaches a of f of x to be equal to f of a. And that can fail in a handful of ways. That limit might fail to exist through any of the means we've seen limits failing to exist. Or that limit may exist, but it could be different from the value of the function there. And kind of each of these classic examples of discontinuity correspond to one of those things failing, or maybe multiples of those things failing. Okay. So I think what I would like to do, give me just 1 second to try and find a nice example. Let me pull up your textbook. Let's do it like that. section 2.5. Here we go. Right. So continuous at some number a in the domain if this limit is equal to the value of the function there. And like we said, this can fail in multiple ways. This limit could fail to exist, or this limit could exist but be different than the function value. The other possibility is that this thing doesn't exist. F of a itself may not exist. There may not, a might not be in the domain of the function f. Now, if I take this and I try to parse it in terms of the delta epsilon thing, so first let me get what we just said down. We need the limit as x approaches a, f of x to be equal to f of a. If you kind of want it in one line, there it is. This is what it means to be continuous at a. And like we said, this can fail in 3 ways. First, the limit as x approaches a of f of x may not exist. Yeah, maybe the left limit is different from the right limit, or you oscillate really wildly as you get close to a without the amplitude decaying. F of a itself may not exist. Right? This would mean a is not in the domain of F. And then thirdly, it's possible that both of those objects exist, but they're not equal to each other. Okay. What I would like to do now, we'll look at examples of this stuff in a minute. I'll show you exactly what it looks like when these failure conditions show up. But I would also like to get us the rigorous definition of continuity from this definition, a rigorous one. Now this is fairly rigorous. There's nothing wrong with it, but the delta epsilon one. Remember that lim x to a f of x equals L means for every epsilon greater than 0, we can find a delta greater than 0 such that the absolute value of x minus a being less than delta implies the absolute value of f of x minus, now this is usually where we would put an L, but here what I have is that the limit is equal to f of a. So f of x minus f of a is less than epsilon. That's the only difference. But you swap the L for f of a because you're saying not only does that limit need to exist, it needs to be equal to f of a. So this is what it means to say that f of x is continuous at x equals a. And it's equivalent to the blue box up above. Some blue as well. Right? And really all we're saying here is the same thing as the limit statement. I'm saying that if somebody gives me an epsilon window about f of a, that we can keep ourselves within that epsilon window by forming a sufficiently tight delta window about A itself. Let me use a different color. All right. The only thing that's changed between this continuity definition and the limit definition that we saw before is that L is f of A. That's it. That's it. That's the only difference. So whereas before this point could be open and the definition would still be satisfied, now that point needs to be closed, needs to be filled in. And we're saying as this epsilon window shrinks, the delta window shrinks with it. So no matter how small the epsilon window is, I can find some corresponding delta window that will keep me keep my y value within that epsilon window. That's really it. So there are some obvious examples to play with, and there are some not so obvious examples to play with. The obvious examples to play with are like piecewise functions that are a little bit wonky. And then piecewise functions that are a lot of bit wonky. And of course, rational functions, things that have vertical asymptotes. So let's play with this a little bit. Let's take ourselves a couple of examples. Detecting discontinuities. Let's look at B right here. Maybe we'll do all of them. Where are each of these discontinuous? I'm just going to write this down. I'll say identify and classify discontinuities for the following functions. F of x equals -x times 2 over x times 2. I'll use different labels. 1 over x squared. 0 All right. So let's start with it. I'm going to identify and classify any discontinuities for each of these functions. I'd also like to sketch a graph for each of these, I think. That'll be useful. And then we'll try to understand the discontinuity in terms of the delta epsilon definition as well. Beginning with this function up here, little f, where do you think this thing might be discontinuous and why?
At x equals 2, because then it becomes undefinable.
Yeah, certainly this function is not defined when x is equal to 2, right? 2 isn't in the domain. So definitely we are discontinuous. At x equals 2. Why? Because f of 2 does not exist. I'm not even worried about the limits. When the number is not in the domain, you cannot possibly be continuous. All right, what about g? I think it may be helpful to graph this. In fact, let me hold on. Before we move to g, I'm sorry. Before we move to g, let's classify the discontinuity at x equals 2. So is it going to be an infinite discontinuity, a removable discontinuity, a jump? How would we do that?
Removable?
It might be. So how would we discern? What I would,
Cancel the common factor x minus 2.
very good. Yeah, I'm gonna. Sorry. Maxwell, baby. Get on the road. Right. Yeah. As Ethan was saying, sorry, my dog just peed on the road. If we factor the top, you'll see that it actually has a factor of x minus 2 that we can cancel with the bottom. So that's exactly what we want to do, which means Sarah's correct. The discontinuity here is going to be removable. That top factors as x plus 1 times x minus 2. And the bottom is just x minus 2. So we cancel these. And we see that this function is actually equal to x plus 1, but only if, now this is for all x's not equal to 2. So the graph of f here, let's see if I have the space, I don't. The graph of the function f here looks like this. It's the same as the graph of y equals x plus 1, except it's undefined when x is equal to 2. And we would classify this as a removable discontinuity. Because if I were to define the value of the function at 2, if I were to separately define f of 2 to be whatever the y value of this whole is, then I would fix the discontinuity. That would take care of our problems. But as is, there's a removable discontinuity there. All right. G, I think for this one, we'll want to look at this in order to talk about the discontinuity. So maybe I'll draw the graph of G. I'll put it over here. This is kind of a funny looking thing. Is a piecewise defined function. It looks like 1 over x squared anywhere aside from at x equals 0. And we know 1 over x squared is a rational function. This graph looks like this. This is certainly one we should know. And it's a power function. But then also define x of 0, or sorry, g of 0 to be equal to 1. So that's the graph of g of x. What kind of discontinuity do we have here? So the first function, we said that's a removable discontinuity. This guy is discontinuous at x equals 0, right? That's the only spot where this thing has problems. The reason I have a separate piece here and a separate piece here is because of what happened at 0. Yeah, very good. The asymptote there. And I'm sorry, I didn't see the other comments in the chat. Yeah, this is an infinite discontinuity. Exactly. So because these guys are blowing up to infinity, because the behavior here is an asymptote, a vertical asymptote, we would call this an infinite discontinuity. All right, h of x, this guy, he's the same as this guy, but we've defined the function to be equal to 1 when x is equal to 2. So we drew the graph of that function earlier. This one is very similar. Graph y equals h of x. Still discontinuous, right? This still has a removable discontinuity.
Removable.
Very good. Yep. And we could fix that discontinuity by changing this 1 to a 3. We could make h of x continuous everywhere specifically at 2 by redefining h of 2 to be equal to 3, because that's the value of the limit there. All right, and this last guy, this is that greatest integer function or floor function that we saw in Eugeni's lecture. And we know it is discontinuous from 1, 2, 3. There's a piecewise constant function. This graph, right? And so on. You can extend it over here to the negative reals also. Just following the same pattern. So where do we have discontinuities here, and what type of discontinuities are there? Yeah, at all of the integers. Discontinuous at every integer. Right? Because at every integer we make a jump. And my choice of language there gives away the classification. What kind of discontinuities are these? Yeah, they're jump discontinuities. So jump discontinuities are what you have when your left and right limits don't match. Removable discontinuities are what you have when you've got a hole where the limit exists, but the function value doesn't match the limit value. And then an infinite discontinuity is a number in your domain or not, where your function blows up to infinity, where you have a vertical asymptote. In terms of the delta epsilon stuff, let me look at the function h a little more closely. And then we will so if I use the delta epsilon definition of continuity, what would that say? Well, here, let's just put in the pieces, right? I know that h of 2 is defined to be 1. So we would be saying for all epsilon greater than 0, we can find, or there exists, a delta greater than 0 such that if the absolute value of x minus 2 is less than delta, then the absolute value of h of x minus 1 is less than epsilon. We'll redraw the picture. So this is down here. So here's a little epsilon window about 3. Here's a little epsilon window about 1. Really what we're asking is, can we keep the function inside this epsilon window by staying close to 2? By staying inside some delta window? The answer is clearly no, right? If you even take epsilon to be 1, then this is the epsilon window, right? It's centered at 1, it goes up to 2, and it goes down to 0. For that particular choice of epsilon, there is no delta that works. Make epsilon equal to 1. And here's your epsilon window. Is there a value of delta that will keep you within that epsilon window as long as you stay? I would say take epsilon equal to 1 and observe that unless x is equal to 2, i.e. absolute value of x minus 2 is equal to 0, then any x value like say this one, will return something outside that epsilon window. And any x value close to 2 will return h of x bigger than 1. Right? In fact, bigger than 2. Even if I'm not here, right? Contradicting the absolute value of h of x minus 1 is less than 1. Right? Or another way to say this is that the absolute value of h of x minus 1, or I'll write it here as h of 2, less than epsilon. We're taking epsilon to be 1, and h of 2 is itself also 1. So this would say absolute value h of x minus 1 is less than 1. Just the same as saying negative 1 is less than h of x is minus 1 is less than positive 1. And then add 1 everywhere, the same thing, 0 is less than h of x is less than 2. And that's exactly what I've drawn here, right? This is that epsilon window. It goes from 0 up to 2. So what we're asking is, can we find a delta such that if the absolute value of x minus 2 is less than delta, then h of x will be between 0 and 2. But no matter how small you choose delta, all y values on this graph, except this one, are outside that epsilon window.
It's very nice.
Making sense? Are we feeling a little more comfortable with deltas and epsilons? So basically, if you want to get comfy with this sort of stuff, what you really need to do is practice with what are called quantifiers. The for all and we can find or there exists. To show that a statement like that, for all epsilon, there exists delta such that blah, 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 you have to just demonstrate that for at least one epsilon, there does not exist a delta. And that's what we've shown here. So that if you take epsilon equal to 1, even that big epsilon equal to 1, there is no delta that works.
Could you explain the last step again?
So let me address these two things. There's something in chat there. We're a little bit uncomfy with the absolute value stuff here. So in the highlighted portion right now, h of 2 is 1, right? That's the definition of h at 2. And then we're taking epsilon to be 1. So I'm plugging in 1 for epsilon here. So I've just plugged in h of 2 is 1 and epsilon is 1. That's the first step. Going from here to here is the a fact of absolute value, right? So the rule is that if you have the absolute value of some stuff is less than a, what this means is that negative a is less than that stuff is less than positive a. That's what it means.
Why the epsilon is equal to 1 here?
Yeah, so I'm taking epsilon to be 1. So this epsilon is this one. And this h of 2 is this one. Remember, what we're trying to do is we're trying to show that this statement is not true. And the way you show a statement like that is not true is by demonstrating an epsilon for which we cannot find a delta. All right. Yeah, and then here, this is just some straight up algebra. So what we're trying to say then is, if I take delta sufficiently small, that is, if I keep x sufficiently close to 2, can I keep h of x between 0 and 2? And clearly from the picture, we see that's not the case, right? No matter how small you take delta, I could use for my x here exactly the halfway point between 2 and 2 plus delta. And then h of that is going to be way up here, which is definitely not in this blue window. So we can be really explicit about this. And no matter how we choose delta, at x equals the midpoint between 2 and 2 plus delta, which is to average those 2.
Excuse me, are you set limit x approach to h of x is equal to h of 2, so that you have the equation of absolute h of x minus h of 2 is less than epsilon.
Yes, so if we wanted to say that, so I think there's two kind of things going on there, right? I'm still having trouble connecting this to the graph. Okay, so here's the thing that my limit is supposed to be equal to, right? So my limit is supposed to be equal to the function value. And the function value there is 1. So what I'm doing is I'm drawing an epsilon window around that. I've chosen epsilon equals 1 to yield my contradiction. I should be able to find a delta for every epsilon. I'm going to show you that for the particular choice 1 of epsilon, there is no delta, which works. The value of the limit is supposed to be 1, right? The limit as x approaches 2 of h of x is supposed to be the value of the function there, which is 1. So what we're doing is we're looking at an epsilon window about 1, and we're showing that even with this large epsilon window, epsilon equals 1, there is no delta window, right? There's no amount that I can shrink these purple things in to keep the graph inside the blue window. So no matter how tight I try to shrink in here, there will be portions of the graph out here which are outside of this blue window. And this blue window is the window from 0 to 2. Right? This little dashed blue line down here is y equals 0. This little dashed blue line up here is the line y equals 2. So what we're saying is, if the absolute value of x minus 2 is less than delta, is it true that h of x is between 0 and 2? And what we're going to show is no, it's not. No matter what you use for delta, this won't work. And yes, that will prove discontinuity. So what I'm doing is I'm taking for my x here the midpoint between 2 and 2 plus delta. So I'm going to average those guys. All right, 2 plus delta all over 2. That's this. Now 2 plus 2 is 4. 4 over 2 is 2. So this is the same as 2 plus delta over 2. No matter how we choose delta, at this x value, h of x is h of 2 plus delta over 2. And since that's not equal to 2, delta is positive, so delta over 2 is positive, so 2 plus that is a little bigger than 2. We're using this other piece. We would get that plus 1. Right, that would be 2 plus delta over 2 plus 1, because h of x is equal to x plus 1 for all x is not equal to 2. And this is 3 plus delta over 2, which is not between 0 and 2. Right? What I'm saying is, for this particular choice of epsilon, no matter what you use for delta, I can find a point between 2 and 2 plus delta on which the graph is outside your epsilon window. I could have used epsilon equals 1/2 or epsilon equals 3/4 or epsilon equals 1.5. Any of those would have worked. I would still get something outside of this. So kind of here's the money, right? This thing, h of x minus h of 2 is less than epsilon, is equivalent to saying h is between 0 and 2. Then what I should have is, if x is between 2 and 2 plus delta, then h of x is between 0 and 2. If I take x to be the midpoint between 2 and 2 plus delta, I could have chosen any point in here, but I need to specify one. So I choose the midpoint between 2 and 2 plus delta. That is 2 plus delta over 2. Then h of x there is bigger than 3. Right? This is a number which is larger than 3, definitely bigger than 2. So h of x is not between 0 and 2 at this particular x value, which, yeah, contradicts the definition, proves discontinuity. So this would be a fairly clean proof that this function is not continuous at x equals 2. Something you should think about: how does this differ from showing that h of x has a limit at x equals 2? Well, if this doesn't work, should that not work? Well, look at the graph. The limit as x approaches 2 does exist here. The catch is that it's not equal to this. And that's how you connect back to the other definition of continuity. If this is L equals 3 would work fine. We wouldn't run into this. But if this is supposed to be 1, then we do run into trouble. Okay, I think that's enough beating you to death with deltas and epsilons. There is something else we need to talk about here today. And those are limits at infinity. Let me just take a quick look through. I don't think there's anything else that we're missing. Oh, there are some theorems. Yeah, left continuous, right continuous. Yeah. Okay, so let me wrap up 2.5 with a few quick theorems. Definitions. Left and right continuity are not things I'm going to beat you to death about, but you'll hear people talk about them. So f is continuous from the left at x equals a means a normal continuity would say lim x approaches a, f of x equals f of a. Left continuity, or continuous from the left, just replaces that limit with a left limit. All right, so to say f is continuous from the left, or left continuous, means that the limit as x approaches a from the left is equal to f of a. And you can swap the word left for right. F is continuous from the right at x equals a means you just swap the left limit for a right limit. Lim x to a plus f of x equals f of a. And so an immediate consequence is that you're continuous full stop at x equals a if you're both left and right continuous. Okay, theorem. If f and g are continuous at x equals a, then so are f plus g, f minus g, f times g, f over g, as long as g of a is not 0. And the fun one, the composite function. Well, actually, let me leave the composite option out. We'll state that separately. It requires slightly different hypotheses. So in other words, combinations of continuous functions are continuous. And simply, we could prove this using the delta epsilon definition. We could prove this using the limit definition, the kind of simple one, and the limit laws. Let me do that. We don't get lost in the quagmire of deltas and epsilons. F plus g continuous at x equals a means that the limit as x approaches a of f of x plus g of x is equal to f of a plus g of a. Also, the limit as x approaches a of f of x plus g of x, according to the limit laws, is the same as the limit as x approaches a of f of x plus the limit as x approaches a of g of x. This is by the limit laws. And now, since each of those functions is known to be continuous at a, this guy has to be f of a, and this guy has to be g of a. This is because f and g are continuous at x equals a themselves. Right? The definition of f being continuous at a is that this limit, lim x to a of f of x, is equal to f of a. And this is what we wanted to show, right? It's like two steps. Use the limit laws and then use the continuity of each. All the other parts go similarly. F minus g, f times g, f over g, all go the same way. Yeah, you just use the limit law and then use the continuity of the individual function. That's the proof. All right, so combinations of continuous functions are continuous. Something you should remember. Another theorem? If f is continuous at g of a and g is continuous at a, then the composite function f circ g is continuous at a. This is slightly different hypotheses than the previous one. Proving this is best done with the delta epsilon thing. I don't know if it's a good use of our time to do that right now, so I'm not going to run through the proof here. use the delta epsilon definition. It's not bad. It's really not bad. But I want to get to some more good stuff for us today. The last theorem I need to share with you regarding continuity is a consequence of one of the theorems in the previous section.
Excuse me, I have a question because right now you are proving those definition is continuous. But in the homework I saw it's different from right now we are learning. So how is it the exam?
Well, so the material that we're talking about today is going to show up in the homework that I'm going to release today. So there, maybe I'm not quite understanding the question.
I just want to ask about the exam. The exam will the same with the homework in website, or will proving some things on the papers and turn in the draft?
I won't ask you to prove much on the test. Yeah, the test is going to be more about coming up with these examples or doing calculations. I may ask you some kind of qualitative questions that are related to this logic as true-false questions, but I wouldn't ask you to construct a whole proof on the test. There isn't enough time for that, I think. So here's the last theorem I want to share with you from this section. Polynomials are continuous everywhere, everywhere. And you remember Yuping's lecture on Friday of last week, where she showed that, a polynomial, you can always calculate the limit just by plugging in. An immediate consequence of that is that polynomials are continuous everywhere. If the limit is the same thing as you get when you plug in, that's the definition of continuity. And the same thing is true for rational functions, as long as you're looking at a number that's in the domain, a number that doesn't make the bottom zero. So polynomials and rational functions are continuous everywhere they are defined. These can be useful when you're answering questions like, yeah, there's a theorem. I give you a function, I ask you, where is this thing continuous, right? Like this, where is this continuous? Well, okay, it's made up of pieces that I know are continuous. The natural log is continuous as long as you stay away from negative numbers and zero. Arctan is continuous everywhere. And the downstairs here is a polynomial. So here they've listed some things that are continuous everywhere they are defined. And that's a reasonable way to think about it. Can you not see the textbook? My side says it's sharing the textbook. Let me turn off the share and turn it back on. Sometimes it gets weird like this. Yeah, okay. So the last theorem here, your textbook actually gives you a sort of broader list of things that are continuous everywhere they're defined. Basically all the nice functions you know, right? All the nice functions you know are continuous everywhere in their domain. And then the last little theorem here is that composite functions are continuous. This is saying the same thing. Composite functions are continuous. All right.
I have a question for the rational function. You see, you just show x square minus x minus 2 over x minus 2 is one kind of rational function.
Let me tab back over here. What were you asking? So,
I just want to make sure what is the rational function. Is it a x square?
Rational functions are ratios of polynomials. So anything like a polynomial over another polynomial. So positive integer powers of x with constants up front, top and bottom. So you can't have a variable under a square root, no trig, nothing like that. Just a polynomial divided by another polynomial.
A rational function maybe will has a hole on the graph, right?
Yep.
So if there has a hole in the graph, it means about the number is not in their domain. So if okay.
Yeah, that's the sneaky thing, right? They're continuous at every real number in their domain. So anything that makes the bottom 0 is automatically not in the domain. And holes, vertical asymptotes, all of those sort of nasty behaviors come from places where the bottom is 0. So yeah, what you said is exactly correct. All right, there's one more thing I want to show you guys today before we leave. We'll get more practice with it on Friday, but I want to at least expose you to it so you can understand it when you see it in the new homework that I'll be sending today.
We already have homework in the website, so we will have the other homework today.
Oh, wait, let me think. So you guys are doing just one homework set per week, right? Do I have you guys doing 1 or 2 per week? I think that you guys were just doing 1.
Said 1.
Yeah, okay. So there won't be a fresh homework today. I think you'll already have some limits at infinity stuff in your homework then.
Also, question about the homework.
Mhm.
Since we don't have class on Mondays, the web assignment going to be due on Monday still or next Wednesday?
I'm trying to make a decision about that. I was originally leaning towards yes, definitely still do on Mondays, so we can kind of keep a regular schedule. So that's the plan for right now, is to still have it be due on Monday, but I'll make an announcement on Canvas if that changes.
Okay, thank you.
All right, so last thing I want to share with you guys, limits at infinity. Basically, these are like horizontal asymptotes. We say that f of x has a limit x to infinity, f of x equals L, if the intuitive definition is if f of x can be made arbitrarily close to L by taking x sufficiently large. The more rigorous definition would be if for every epsilon greater than 0, we can find n greater than 0 such that the absolute value of f of x minus L is less than epsilon whenever x is bigger than n. So it's a little bit different than the limit at a finite value. This looks sloppy. This is epsilon. And kind of the picture here is that you can keep yourself trapped in this epsilon window about L. This time not by staying close to some particular finite number, but by staying far away enough from 0. So in other words, if I can keep you in this blue window by walking sufficiently far to the right, and I can do that for any size blue window there, then I would say that that is your limit at infinity. So here would be capital N. If you take any x value to the right of this, you'll stay within this blue window. And as you shrink this blue window down, N goes off to the right.
So L in this case is the value of the horizontal asymptote?
Exactly. So limits at infinity are the same as horizontal asymptotes. That's the take-home message. So limits as x go to plus or minus infinity are the horizontal asymptotes. It's possible to have different ones, more than one. Function F. That's it. That's a nice intuitive way to kind of understand what a limit at infinity is. And I think that that's a good spot to stop for today. So on Friday, I'm going to come back and show you lots of tricks for calculating limits at infinity. We'll get a little bit of practice using this epsilon n definition, coming up with n for an arbitrary epsilon. But mostly, I just want you guys to get comfy with the ideas. So a limit at infinity is indeed the same thing as a horizontal asymptote. And then on Friday, I will show you a little bit how to do those calculations. Alrighty, if you do need to talk to me about anything, you come by office hours, send me a Canvas message, go on the Discord. All of those are good. And please just watch WebAssign closely for any due date changes. If I make changes, I will also make an announcement on Canvas. But yeah, no class on Monday, so just be mindful that the due dates may change.
There is no class on the next Monday.
Correct. Yeah, next Monday is a holiday.
And also, which chapter will you teach in Friday?
So Friday, we're going to do more 2.6. We're going to do more limits at plus minus infinity. That's the last thing I have planned for this week. I think that's the last topic I have on the syllabus for this week. Yeah. So on Friday, we'll probably do a few continuity problems, kind of get you some more practice with those. And then we'll talk about limits at infinity. I may introduce some of this stuff for next week, but mostly 2.6. Mostly this section.
Thank you.
What time is office hours today?
1 to 2.
Awesome. Thank you.
That's it. Then I'm going to go ahead and end the meeting. Hope you guys have a good rest of your day, and I'll see you on Friday.